So here's the relation matrices, which is 9.6. Why it's need to study relation matrices? Because we have studied generators and relations. So it's because it's easy to manipulate just the coefficients as the row of a matrix. If we have m relations in n variables, the relation matrix is the m by n matrix whose are the coefficients of the successive relations. How, for example, as you can see on the screen, these are the set of the relations in form of linear combination. We can code it as a 2 by 3 matrix, which is 3, 7, 4, 0, -5, and 9. Here we can use the notation to provide a convenient way to representing abelian groups that are given in terms of generators and relations. We simply write the relation matrix and to show that we have in mind in the abelian group and not just the matrix. We use square brackets instead of the usual parentheses. A is an m by n integer matrix with this being the entry in the ij position. We can denote it like for square brackets using square brackets, so we can write our equation in form of this, and it's as similarly it's isomorphic to these. It's for x and for y. So generally we use three variables, which is x and y and z. In this recording we do the next example. So here's the example related to the representation. 3, 2, 7, 4, it's a matrix 2 by 2. I can write in the form of the equation like this. 3x plus 7y, which is equals twice of x plus 4y equals z. Here's the elementary integer row operations and elementary column operations. What they basically are, we represent an abelian group given in terms of finitely many generators and relations by a matrix. And we use elementary row and column operations to simplify it. These operations are very much like the elementary row and column operations from the linear algebra, except that we don't allow multiplication or division by a constant. As you can see, the first, second, here we are swapping the rows, changing the sign and subtracting with k times from any row. And similarly for the column. As you can see the example on your screen, which is 3, 2, 7, 4 in a 2 by 2 matrix. Here we swap the two rows, which means we are swapping the relations. Now the next example is 3, 2, 7, 4, which is isomorphic to this. Here we swap the relations. So of two columns. Strictly speaking, these groups aren't equal because in one group 3x plus, as you can see here, it's a 3x plus 7y equals 0, 2x plus 4y. And in this relation, for this matrix, it is 7x plus 3y. These are isomorphic to each other but not equal. And the relation, we can define it as, it's an simple equation which is given by swapping the columns, we'll get this relation. The next example is 3, 2, 7, 4 equals 23, 2, 47, 4. What we have done here, we've added 10 times row 2 to row 1. How? Here we can see it's a simple equation, 3x plus 7y plus 10th of twice of x plus 4th of y, which gives us 23x plus 47y equals 0, as you can see here. What we have done here, we have added this equation to 10 times of this equation. So we will get this. As we studied the elementary operations for the relation matrices, so we'll apply here these relations. So the new equation is the consequence of the original two, right? And we can see that these are the identical to each other but not equal. So these are the two sets of the equation. Here next we have a theorem which says that if a matrix B is obtained from a matrix A by a sequence of elementary row and column operations, then uh, matrix A is isomorphic to matrix B. It is more similar as we have did the examples. So here we have to prove it. Let G equals this, as we have studied this formation too, where Ri is the linear combination of this, and let A is equals Aij, which is the uh, formation of coefficient, be the matrix of the coefficients. So it's clear that the elementary row operations don't change the group. All they do is to change one set of relations into an equivalent set of relations, as we have seen before. The column operations are a little more difficult to see since we need to change the generators. So here, as far we have studied, we can swap the generators, we can replace, the column has the effect of replacing, and we can multiply with the coefficient and subtract from any row, any column which we want. This is the proof, as you can see on your screen. Suppose we define new generators y1 till yn by yi is equals xi if I is not equals j. And the another one is yj, which is equals xj plus kth of xi. Right? It is clear that new generators will generate the group because we can express the old generators in terms of the new ones. As you can see, xi is equals yi. If we change the position. We have changed the position. Since xj is equals yj minus kth of xi, yi, ky. Now suppose that the another relation is a relation between the old generators. We can write this as am1x1 plus till ai. We have changed our coefficient. Here the omitted terms are all have the form a and xn. Expressing this in terms of new generator, it becomes. So the final result is expressing all the relations in terms of these new generators. The coefficient matrix has k times column j subtracted from column I. Simply, we have changed our old generators. So these are the representation how to write the equation, right?